It's being recorded. So today we started gas laws, and I'm started off with a simple question, which is uh, to list down the physical characteristics of gases, and then talk about and give a unit that we use to quantify or measure that gas. So a unit in which that physical characteristic is measured. I gave an example, which is pressure. Oh, sorry, I gave an example which is volume, and the unit of volume is liters, and then I asked the students whether they can list three other characteristics of gases. So now I'm just collecting the answers, and you'll be able to see the answers on the next slide. I'll pause it here until I get the answers from the rest of the class. Thanks. So as you can see, the physical characteristics that the most common physical characteristics that we use to characterize gases are volume, pressure, temperature, and the number of atoms. Now, on the right hand side, you're given the units that we measure volume in. It says liters, but in chemistry, we tend to use centimeter cube or meter cube just because they are these SI units or international system of units. We follow the SI unit, SI system of naming, or SI system of units. So that is the reason that we use meter cube or centimeter cube for volume. For pressure, we use Newton per meter square, and we call it pascals. For temperature, we'll use Kelvin. We don't use degrees Celsius or Fahrenheit in chemistry. So if you're given an answer in degrees Celsius or Fahrenheit, you would have to convert it to Kelvin, and you do that by adding 273.15 to it. So anything that's given in degrees Celsius, you want to convert it to Kelvin, just add 273.15 to it. Last but not least is moles, and we already know that mole is just, it tells you how the quantity of a gas. So 1 mole is 6 times 10 to the power 23 atoms of that gas, or 6 times 10 to the power 23 molecules of that gas. So volume, pressure, and temperature we already know, and number of moles is just the amount of the gas. So once we know this, we can move on to the first gas law, which is Boyle's law. So I've put an image on the board, and I want you to do a see, think, wonder on it. A see, think, wonder is just, looking at the picture, then just telling me what you see, what you think about it, and then what are your questions. So I'll give you 3 minutes to work in teams. I'd like to see groups of 4, and right now not everyone is sitting in groups of 4. So if you could please sort yourselves in groups of no less than 4. I don't even mind if it's 5, but no less than 4. That really help. So your time starts now, 3 minutes. So you would have noted from the figure that as the pressure increases, the volume decreases. Now mathematically, you can write this down as you can write this down as P is inversely proportional to 1 over V. Now, we can also change the proportionality sign to an equal to sign, but as you remember from studying inverse and direct proportional, that changing this to an equal to sign would mean that you introduce a constant into the equation, which gives you P is equal to K over V. Now, that also means that if you remember a little bit of algebra, you multiply both sides by V, and you get P V is equal to K. This is called Boyle's law, which basically means that if you have a system at a certain temperature, now temperature has to be fixed. Temperature is fixed. If you, let's say, had this piston, and you were exerting a certain pressure on it by adding weights, like you saw in the figure. Let's say it was 4 atmosphere, and let's say the volume was V. Then if you retained the same temperature, if the temperature was the same, and you decrease the pressure to 2 atmosphere by decreasing the weights on it. And if I asked you what would be the new volume, you would just need to know that since it's Boyle's law, the pressure times the volume will be the same, will give you a constant, which would be the same here. So if you had to do this mathematically, you'd say, let's change this to numbers. Let's say this was 2 liters, and we do not know what V2 is. We don't know what that is. We know that P2 is 2 atmosphere, P1 is 4 atmosphere, V1 is 2 liters. I just want to figure out what would be the value of V2. We know from Boyle's law that PV is equal to K, which basically means that the product of pressure and volume in the first case would be the same as the product of pressure and volume in the second case. The pressure in the first case was 4 atmosphere. The volume was 2. The pressure in the second case is 2 atmosphere. And the volume is, I don't know. So 2 and 2 cancel out. That gives me V2 is equal to 4 liters. Which of course makes sense, because when you decrease the pressure, you expect the volume to increase. So Boyle's law tells us that if the temperature is constant, if T is constant, temperature is constant, then the product of pressure and volume for pressure and volume will be constant.
Is this for all gases, or is K different for every gas?
K would be different for different gases, and we'll get to that. That's when we talk about the ideal gas equation. So we'll get to that. When you're conducting an experiment, or when you're checking the product of pressure and volume, obviously if the gas is different, you'd expect the constant to change accordingly. So when we're doing the experiment, we are doing it with the same gas. If we are compressing air, we are compressing air. If we're compressing oxygen, we're compressing oxygen. We wouldn't do, let's compress air in one and let's compress oxygen in another, and the results would be the same. It wouldn't be. Okay, so that's the first part of it. You have taken this down. Let me move on. Next bit, which is a discussion on Boyle's law again. So Boyle's law says that pressure and volume are inversely related, or PV is equal to K. As one goes up, the other goes down, and we expect that to happen. You increase the pressure, the volume would go down. You decrease the pressure, the volume would go up. Right, Rudy? Yeah. So diagrammatic representation of that. We've already done this. Same thing. It's a inverse proportionality. That's why you see the graph is a rectangular hyperbola. Yeah. Now the next one is Charles' law. Again, I'll give you 3 minutes to talk to your partners, to talk to your team about what you see, what do you think is going on, and what does it make you wonder. So have a go at it. Thanks. Okay, so the answers to the questions were, what do you see? I asked my students, they said that they saw a weight, they saw pistons, they saw atoms, they saw a linear curve. What do you think is going on? I got the answers that as the temperature goes up, the volume of the gas inside that piston would go up. That kind of makes sense. And then the question that was asked was, what about the pressure in this case? Well, the pressure in this case would be constant. So now what I'm going to do is, in OneNote, I'm going to derive the formula, show you how this how we came to this formula that we are using. So let's just quickly derive it. So Charles' law. Mr. Charles. So Charles' law, mathematically, we can say that V is directly proportional to T. That means as you increase T, V goes up. Now, this can be written as V is equal to K times T. All good? Or divide both sides by T and we get V over T is equal to K, which is a constant, or V1 over T1 is equal to V2 over T2. Now, remember, pressure is constant for Charles' law. Now, if you're wondering how is this any useful, we will get to problems where you'll learn how useful this can be. Are you ever going to use it in real life? Probably not. Okay, so moving on. Yep. Okay, so moving on from Charles' law, just to show you a few slides here. So Charles' law states that volume of a gas varies directly with the absolute temperature at constant pressure. Now, you do need to remember temperatures in Kelvin. I'll say it 1,000 times, I'll say it 1,000,000 times, yet there are mistakes in the exam. Temperatures in Kelvin. Think of it in this way. V1 over T1 is equal to V2 over T2. If temperature was in Celsius, you would have to probably replace, let's say it was 0 degrees Celsius. Then you would have to put a 0 and that would make the whole formula obsolete. I mean, there's no point, then you can't use this formula. 0 degrees Celsius, however, is 273 Kelvin. So you can solve it using the absolute temperature, but you can't do it in Celsius. So think of that exception, think of 0 degrees Celsius, and you'll know that you have to substitute it in Kelvin. Again, just a diagrammatic representation. All good with this one. Now, last one is Avogadro's law. I'm going to leave you with the same question. What do you see? What do you think is going on? And what does it make you wonder? I'll give you 3 minutes for this again. So we did a see, think, wonder on Avogadro's law, and the answers that I got was, what do you see was, what the students saw was there was 1 mole of gas in one cylinder, 2 moles in another cylinder. They also saw that there was pressure being acted upon on both cylinders. What did it make them think? They thought that as you increase the number of moles of gases, the volume of the cylinder increases. And finally, the question that was asked was, why is the pressure the same? Why is the pressure constant? And the answer to that is that the cylinder's volume is increasing to keep the pressure the same. Now, I wanted to quickly derive Avogadro's law as well. So I'm going to quickly do that on OneNote. So Avogadro's law is mathematically we can write it as V is directly proportional to N. What needs to be the same? Pressure same, which can be written as V is equal to Kn, which can be written as V1 over N1 is equal to V2 over N2. And oops. And that is your Avogadro's law. Quickly going through the slides for Avogadro's law. So at constant temperature, the volume, that was at constant temperature, and we have been working with constant pressure. Wait, so, yep, I know. Okay, so quickly, sorry for the confusion, but it has to be constant temperature and pressure. So in the OneNote, you'd have to write constant pressure as well. So that's the end of Avogadro's law, and we'll continue